I'm going to be talking about developing autonomous agents to learn and plan in simulation and in the real world. There we go. So there are many large challenges in the areas of health, our safety and our use of time, and our efficient use of resources. The beneficial impacts from working on improving healthcare can increase our life expectancy and our overall well-being. One example of this is being able to develop an assistive robot that can help support people in their homes and their daily lives. Similarly, on a normal year, we would use many types of transportation, all that involve different levels of risk that we would like to be able to mitigate. And last, if we can use our energy more efficiently, we can reduce the amount of waste and the environmental impacts that we have, potentially by using more online adaptive types of learning systems inside of these particular energy types of environments. So while learning systems can help across these problems, I'm going to discuss the challenges in developing this type of home service robot today to motivate a lot of the problems that I'm particularly interested in. So if we want an agent or a robot to be able to operate and work with us, it's going to need to be able to solve a large number of tasks every day. And on top of being able to solve many tasks, we have each of us different homes with different layouts and appearances, colors, styles. And then for an assistive robot to really be capable and kind of taskable inside of these environments, it's going to need to be robust to all this diversity that naturally exists in our world. If we can develop robots that can learn and adapt, in this case, to each of these new homes they're going to be used in, it will lead to a more general and useful assistive robot system. Especially if we don't want to have to go around and tell the robot specifically what we want it to do in all of the cases inside of our environment that it's working in as well. So what I really want is to develop the base learning system or algorithm that can grow into a truly intelligent, multi-skilled agent that can learn and generalize quickly. But how can we create these sophisticated learning agents? So there's a number of current challenges with being able to develop, such a learning agent that would be, as skillful as we might want. This agent is going to need to be capable of learning how to solve complex planning problems in many different environments. For example, learning how to clean and organize in anyone's home. The agent is going to need to be able to do this while interacting in our real world, learning given very noisy information, limited control over the environment and how it changes. And also last, how can we get agents that independently learn to develop their own skills? So without us having to necessarily hold their hand and tell them exactly what they want them to do and the behavior that we really want them to see, but in particular for them to learn skills that display sophisticated intelligence and control over the environment that they exist in. So today I'm going to present a few methods that focus on these different challenges. So I'm going to start by talking about reinforcement learning, which is basically a framework on being able to optimize policies where an agent can learn through interaction in the environment to find the best actions that it can take in the environment. So this is reinforcement learning is built on top of the framework for a Markov decision process. And in this case, this Markov decision process consists of a set of states. These are all of the states that the environment can be in. A set of actions. These are all the actions that the agent can actually take inside of the environment. A reward function here, which is basically also a way for us to inform and indicate to the agent the type of behavior it should be trying to optimize, and that we really want the agent to produce. A forward dynamics function. So if the agent is in a particular state and it takes a particular action, this determines the probability of the agent ending up in some next state after that action is taken. A discount factor, which really determines how far into the future the agent should care about having to plan. And also an initial state distribution to determine where the agent starts out inside of this MDP. So then how can we go about optimizing a policy in this case for this MDP? So this, one way to do this is to be able to estimate the value of the policy. So you can form basically the average behavior that the current policy is basically showcasing according to the reward function that's built into the MDP. And then you can use this estimate of the average kind of behavior that the policy is currently getting. And you can compute the advantage in this case, which basically says, like, if the agent takes a reward and if the value plus that new reward in the next state is higher than the current state was in, then overall this action that was taken in the environment is at least a small improvement on the current average performance of the policy. And then when one of these actions is found, you can use this advantage in this case as a type of score function, such that when it's found, you can adjust the policy distribution now to instead reinforce this new action that's been kind of found to be better because it has a higher advantage value, to shift the overall policy distribution more towards this producing this action the next time the agent is in this same state, according to this model. So then this is combined in deep reinforcement learning for a lot of the work that I do. So when deep reinforcement learning is being used, basically we use a neural network, which forms a nice large parameterized model, such that we can now do things where you can have an input that goes into this neural network that is basically an image of whatever the robot is actually seeing in this case. This is fed forward through the network, and in this case, you can think of the agent computing a torque that it wants to be able to actuate at that particular state that it's in, and then using the loss that was discussed on the previous slide, where we're trying to update the overall policy distribution, which in this case is being represented as a deep neural network. We can compute the gradients using some calculus in order to be able to figure out how to adjust the parameters in this network in order to have a higher likelihood of producing this better action the next time the agent comes around and visits this state. Great. So why learning through interaction in this case? So one of the reasons that this model kind of works well is that it's also very flexible. So there's no specific need to have to create explicit models of the environment in order to be able to optimize a policy in this case. And it's also can work really well because you can now train a policy in different types of agents through really high dimensional inputs, including using vision in large deep neural networks. And another kind of, it's also good because the reason in some of these environments and in different tasks, it can be very difficult to be able to create explicit models of how things are actually functioning. So in some cases, when operating into these different tasks, it's really difficult to be able to model complex dynamics, things like contact forces, friction, all of these kind of like nonlinear aspects of interacting with the world that can be estimated much better using this more kind of implicit model of just understanding how the dynamics works without having to explicitly model the dynamics in those cases. So I'm going to start by talking about a project on hierarchical reinforcement learning. This is called Deep Loco, Dynamic Locomotion Skills Using Hierarchical Deep Reinforcement Learning. And this was some great collaborative work I did during my PhD at the University of British Columbia and with some other collaborators at the National University of Singapore. So the idea here is we have an agent here that's in this particular environment, and the agent wants to learn how to plan to get to this target location that's on the other side of this obstacle. So we can think, in this case, one of the first things the agent needs to do needs to decide which direction it should go around this obstacle in order to reach this goal location that's on the other side. So then once the agent has picked a particular direction to take around this obstacle, the agent now needs to figure out the long sequence of torques that it needs to actuate all of the joints on itself in order to be able to realize its goal of trying to get to this target location. So this problem is going to be separated into two parts for this work, and it's going to be able to be designed and trained using a hierarchical policy with 2 policies, one for each kind of level of the overall planning problem. So I'm going to start by talking about the low-level part of control here that optimizes for the torques for the agent. So in this case, there's a low-level policy that takes as input a small goal feature, which is the next 2 footsteps that the agent, that we want the agent to be able to achieve, as well as the state of the agent in this case, which is the kind of pose and dynamics of the agent overall. And then, and then the low-level control policy in this case is producing the torques that the agent should, achieve in order to be able to optimize the policy and receive high reward. So then what is the reward function that's being used to be able to optimize this policy? So in this case, it's 2 parts. So the first part here is a little bit more of a data term in this case. And what I mean by this is there's a small collection of motion capture data. And the idea is this motion capture data will help give the agent in the simulation a little bit more natural motion at the same time as learning how to walk, because it's based off of some of these walking motions of people that have been recorded. And then the second part here on the right is the goal conditioned part of the task that the agent wants to learn. So the simulation is going to randomly sample different footstep locations in front of the agent, and the agent wants to be able to kind of, as truthfully as it can, match its footsteps in the simulation to where those goal footstep locations are being specified from the simulation. And then after training this policy using deep learning, you can have a fairly robust agent that's fairly responsive to some of the goal footstep locations that are shown here on the ground as these kind of green spheres that are being highlighted. And up here on the right is actually the value function for the agent that changes according to where the goals are. And overall, training an agent like this, in this case, only takes about a day in order to be able to train a policy that can follow the goal footsteps this well. All right, so one of the great features of being able to train this low-level controller now is essentially the MDP that the high-level controller has to operate in has been transformed. And in many ways, it's been simplified so the agent doesn't have to plan as many detailed steps in order to be able to locomote the overall agent. And now the high-level controller can plan just in the space of these footsteps that we're just discussing. So then let me get into some more details for how the high-level controller is trained. So in this case, the high-level controller policy has some of the same inputs, but some additional ones that are important. So it still has as input the overall pose and dynamics of the character in the simulation. There's now a slightly different goal input that is basically the distance and direction that the current goal is away from the agent. But the last part here, kind of the more important input, is the agent also gets an egocentric vision field of the area around itself, so that it can basically use this as basically an image so that it can determine, finding safe areas in the environment, being able to avoid obstacles, and all in the case of being able to maximize their reward in those cases. And then here, the high-level controller is, in this case, producing those footstep plans that the low-level controller will has already learned to follow. And then the high-level controller reward for this case is the distance between the agent and that target location that's being kind of specified. And then this particular, overall method ends up working out very well. So by well, I mean in this case, can train an agent in just about a day to about 2 days to be able to learn how to navigate environments such as this. So it's using the overall terrain input that's seen here as a bunch of red dots to be able to determine, now that it's found, which are the safe areas that the agent can navigate here in the environment, avoiding running into some of the cliffs and avoiding falling off the edge of this cliff and tumbling to its doom while it's navigating. And then one of the great features of this overall method and deep reinforcement learning is now I can just change the environment to a different one keeping pretty much the entire system the exact same, and the agent can solve tasks in this type of environment as well. So here the agent has learned to dodge a number of dynamic obstacles in the environment using the same reward function, kind of the same kind of inputs, just change the environment in this case. And then so here's another example of that. So here the reward function is slightly changed in order to have the agent kick the soccer ball towards this target location, but the overall reinforcement learning algorithm and setup can now just be repurposed, reused on this different scenario, and the agent can train all over again to be able to solve this task. Sorry. So then how important is the hierarchy in this case? So some analysis is done to show that if we just trained a version of the policy that took in image inputs and would produce the torques in this case, it struggles quite a bit in being able to solve any of the tasks. In particular, even just the soccer dribbling one that doesn't even have the terrain inputs, then is sort of a simpler task that's faster to optimize. But overall, the hierarchy ends up being really important, allowing the agent to be able to solve tasks that have sort of such large planning horizons for this particular overall project and method. So then some of the insights for this work. So as I was just saying, the hierarchies really do help enable long-term planning because it allows us to be able to transform MDPs, in this case, into simpler MDPs that are easier to plan over. Using deep reinforcement learning is very helpful because now we can just provide a bunch of high dimensional sensory info to the agent, and we don't have to worry about crafting any kind of specific state spaces the agent has to learn in such that they're efficient. And we can also just change the environment and use this high dimensional state input, and the agent can still learn in that case without any extra modifications or engineering. In terms of future work, even building on this that I'm very interested in, so one area that I'm already doing some work in is concurrent policy optimization. So for this project, the high level and low level were trained separately, which makes the overall optimization much easier. But in a sense, you can't get as high quality policies as if you could optimize these two policies together at the same time. This, however, is a very difficult non-stationary optimization problem, but I'd be happy to talk more about at the end for anyone who's interested. Also, I'm very interested in learning multiple tasks. So here the agent was trained from scratch across all of these environments on the bottom, but it would be much better if we can construct some more continual learning agents that can transfer between these tasks and kind of, when trained on one, can use some of that information on another one at least. So this gets into another area that I've done a lot of work in, called in the area of lifelong learning. So it really is this idea of, I want agents to really learn reusable and very generalizable skills. And sort of the method is you really want agents to be able to continually learn and grow. The same way that we've experienced tons of things in our lives, gone through many years of education, such that we can learn to be able to apply the skills that we've learned and the information that we've gained to be able to solve new tasks faster or even solve new tasks at all. And in my case, I'm particularly interested in being able to do this without many types of supervision. So often there's separation between the tasks that's well defined so that you can develop different types of meta learning skills because you've got a whole collection of different tasks. But I would like to be able to perform this more naturally the way we do if we were just to put a robot out in the real world that doesn't have a built-in method to separate tasks and just learn this continual learning behavior in that case. So then this gets into my next project that I'm talking about today, which is called ReALMM. This is reinforcement learning for autonomous mobile manipulation. And this has also been some great work that I've done at Berkeley in collaboration with a number of people at Berkeley. So the idea here is to think about, all right, how can we start to train an actual cleaning robot? So in this case, the cleaning robot is this nice little WidowX robot here, where there's essentially one of those Roomba robots on the bottom so that it can drive around a little bit like a tank. It's got one WidowX robot arm on the top of it so that I can go around and interact with things and be able to grab different stuff inside of the environment. And then the way the agent gets to observe the actual environment is just through this RGBD camera here mounted on the top of the robot. So what are the issues here with just trying to apply the same episodic RL that was used in the last project? So for starters, the actions here for this agent do involve a lot of complex movements and navigation. So I mean complex arm movements and navigation. This makes kind of overall policy that you want to be able to optimize and the dynamics fairly complex. It's also not clear how you can calculate the reward now that you're in the real world instead of in a simulation. So in the last project, we essentially had perfect control over the simulation, so we could compute the distance between where the agent was and its goal location without any noise at all and without any issue. But in the real world, this is basically not possible. And then the last part is how do we address some of the issues that have to do with the initial state distribution that I mentioned early on. So one example of this is in the previous project, when the agent is trying to learn to navigate and walk along that kind of like trail in the mountains, if the agent falls off the edge of that cliff and starts tumbling to its doom, it's very easy to detect. The agent can just be reset back onto the trail and maybe a slightly different pose, but overall in a very safe position such that it can continue training. We don't have this type of power in the real world to be able to detect and reset things so easily. And there is a lot of great work that does sim to real training in order to be able to train robots in this area. But one of the challenges, at least with using sim to real training, is you need a simulator that's very realistic, down to some more of the fine-grained details of the dynamics of the world. And this, at least in some areas, this is currently not quite possible, although I do believe that there's a lot of great people working on these physics simulators that they should maybe start to bridge the gap between simulation and reality in the future. And also, in some cases, even if you're using sim to real, if you want to continue training the agent in the real world, you might not have access to the same reward function that was in simulation that is now going to need to be used in the real world. So then how are these different issues addressed? So the actions, in this case, they do involve a lot of complex arm and navigation movements. So here for this project, the policy is actually separated into two policies. One that specifically does grasping, which is shown here on the bottom right, and one that controls the overall navigation for the agent as well. And then the reward that's used for this particular robot in this case is whether or not the robot can achieve a successful grasp. So if the agent reaches out into the world, closes its hand in the world, and then picks its hand up, and then tries to close its hand again, and it can't, it'll be rewarded for basically being able to successfully come up with something inside of its hand. And then in this case, resets are dealt with a little bit differently. So in order to help provide some additional diversity to the training for the agent, which really helps in training some of the deep models, the agent actually is going to perform a type of autonomous reset. So after it picks up an object, it's going to randomly place it down inside of the environment and then drive to another random location. This will add a lot more, as I said, diversity to the overall training set for the robot, and this really helps training. So then we'll start with talking about the grasping policy here. So the grasping policy works by just taking an image, a little cropped image of what the robot gets to see of the ground in front of it. And then in this case, it's training a contextual bandit policy to predict the probability of grasp success for a little local grid that you could think of as laid out down right in front of the robot. And yes, and that's mostly it for the grasping policy. And then we want to be able to train this overall grasping policy using just images and whether or not the robot was successful at making a grasp at that location in the environment. So a small curriculum is used to be able to train the agent in this case. So you can think of it as, the robot is maybe born in this case. It can't quite walk yet, but it can move its arms around. So we start out the robot at a fixed location where the navigation policy is off for a little while and just put an object in front of the robot to learn to practice grasping without having to worry about navigation yet. So then here, so this is sort of the next step in the training now is we now turn on the overall navigation and the grasping at the same time. and they're both trained concurrently at the same time in this case. So then how the policy is trained for this robot is the agent gets to see an observation of the world, decides the type of navigation action that it's going to take in the environment, and then it actually asks the grasping policy, what is the basically likelihood of success if I do attempt to make a grasp at this location? And this is fairly important because we really want the robot to be able to learn pretty quickly and not waste time. So we do want to really avoid attempting grasps in the world that the robot is very confident about, or very confident that the grasp will not be successful, and should really only attempt grasps when there's a real possibility that it'll be successful. So if the robot does say that there's a good possibility of a grasp being successful, a grasp is attempted, and then if the grasp is successful, the robot, as kind of shown here, will pick up one of the objects, do this type of pseudo reset where it drives around in the world, and then places down that object in the environment, and then drives off to another random location in the environment to continue grasping other objects. So then using this method that we've just been discussing, the robot is able to train to be able to perform a lot of these type of grasping behaviors and grabbing objects and moving them around in the world in only about 25 hours. So here it's just sort of the warm-up phase for the navigation being shown. The robot driving around, it's about half done training. And then after 25 hours or so, the robot has gotten pretty good at being able to identify and collect objects and move them around in the environment. So we evaluate this in a slightly different regime. So here now, so during training, a lot of the pseudo resets are performed for the robot to drive around. So then now we can take this like policy that's been learned, put the policy or the robot inside of the room, put a little basket on the front of it, and see how quickly it can now go around and collect all of the objects inside of this room. And then here are 3 different rollouts for evaluation for the robot, collecting objects with different initial configurations of the robot and different objects. Showing some of the rollouts for the learned robotic policy in this case. So here, going to talk a bit about the importance of now being able to train the grasping policy and the navigation policy at the same time. So here I'm actually showing after the robot has been trained to be able to navigate around in the world and grasp different objects, the robot can be instead put back in this initial position how the pre-training was done for the grasping. And it's already possible to see that this has even improved the overall grasping ability of the robot, even in this stationary case. So being able to optimize these 2 policies together not only improves the grasping, it does improve the navigation as well, even in their combination of being able to train at the same time. And then maybe like kind of related to some of the questions on hierarchy, one of the reasons why this training works a little bit better to be able to train these policies at the same time for this robot, it has some to do with the fact that the grasping policy is more of a contextual bandit policy and not a full kind of reinforcement learning policy that's learned to plan over a long sequence of steps. So the non-stationarity that the robot has to deal with when the underlying grasping policy changes is not as significant in this case. And then one of the great properties of being able to use deep reinforcement learning in this case is now we can just change the environment, add some obstacles, make the room a little bit bigger, and then here we can train the agent in this case to be able to learn to go around. And this is it training, be able to grasp additional objects in this case and perform the overall same task in different rooms and different environments. So then some insights for this particular project, and really like about trying to apply reinforcement learning as it is onto these more robotics projects in the real world, is this project, a lot of it was being able to develop this kind of self-contained learning platform. So there doesn't need to be any extra supervision for rewards or any other kind of interventions in these cases to be able to reset the robot. And it can just be kind of placed inside of someone's home for the most part, and go around and be able to clean up, a number of objects and learn how to go around and grasp things and collect them. As I said, it does train with very little supervision, making sort of like the training of this kind of useful also from a research standpoint, because then you can train more of them with kind of like less human effort. But also then we don't need to be so careful about the being able to prescribe the particular types of tasks sort of that it does. And in particular, the only real supervision or intervention that was really applied to this robot in some cases is just to go in and replace the battery on the robot about every 7 to 8 hours when it runs out of battery. So then some future work in this area that I'm really interested in is really being able to get robots to be able to, in this case, clean anywhere and everywhere. So this was in, this work was done in a type of an office environment that ends up working out really well. There's different types of controls that makes it easier for people to be able to work in office environments. But I really want like a robotic system that can operate in a very kind of diverse number of worlds and terrains, in this case, in the real world. I'm also really interested in this type of environment interaction. So like agents that can go around navigating the world, but also actually like change things, relocate different objects, solve different types of tasks, and in the process have to learn sort of additionally complex things in order to be able to perform this interaction. But then we might think, all right, so then what should the agent actually learn now if it can operate in this world with all this interaction? So this gets into one of my next areas of research that I've been working in for a while. So I really want agents to learn very well-defined skills. So in this case, what I mean by that is, we don't want agents that are going to be learned to be basically learning for very specific tasks or very specific reward functions. I really want agents that are going to be able to develop these really sophisticated and well-defined skills. So one example of this kind of being able to show here on the top is to do a type of goal-conditioned reinforcement learning. So this is similar to what was described in the first project where you can have footsteps, but I've done some other work where instead you can provide an image of the environment to a robot that's being controlled and being learned, and then have the robot reconfigure the area in front of it such that it matches that image in that case. And then I'm also very interested in being able to explore task-independent objectives. So one kind of broad skill that we all use very often is types of imitation learning. And this is a skill that probably most agents should be able to facilitate so they can gather some expert behavior just by observing some others. So then basically, how can we build on this a bit more and be able to discover some even more task-independent type objectives beyond just imitation learning? So this leads into the next project I'm discussing today, which is SMIRL. So this is surprise minimizing reinforcement learning in unstable environments. And this is recent work that I've been collaborating with many great people at the University of California at Berkeley. And this is published this year as an oral presentation at iClear. So the idea for this project is to investigate intrinsic rewards. So we do really want agents to be able to develop their own skills in the environment without like anyone specifically or any expert having to go in and tell them exactly what to do. So then what objective should we really use to be able to encourage this type of development? And then this work is going to borrow some ideas from what we believe encourages people to develop. So it's based on some of the work from the free energy principle. And in this particular case, I'm going to be talking about how an agent can learn to minimize surprise. So what do I mean by surprise? Minimizing surprise in this case. So the idea is in the natural world that we live in, there's an enormous amount of things that are causing different types of novelty. So you can think of other agents in the world that are changing things, living their own lives. There's sort of natural amounts of like weather and erosion that are just changing every day. Kind of like the sun rises and goes over night and day, also another kind of different change throughout the environment. And then the idea is for us to survive, we wanted to be able to learn to maintain order in our environment in spite of all of these changes. And what I'm really trying to get to here is I really want agents that'll be able to, basically, we've learned to develop really complex systems in order to support that survival. So you can think of the way that we've learned to develop really large cities, power systems, homes and shelter, all in the support so that we can maintain the order in our environment and have better control over basically what we believe our future state is going to be, so it can minimize the amount of potential chaos into the future. And in these days, we've even learned that, we have to be even more intelligent. Instead of just extracting power however we want, we need to do it far more intelligently, in this case, such that we don't infect the environment as much, so that we can even ensure that our ecosystem is going to be maintained in this process. So then here on the bottom, I'm showing an example of this for a simulated kind of robot. So one example of this is if you had a robot and you put it out in the nature, you would want the agent to be able to learn to go and construct some shelter of some sort so that it can learn to avoid the different changes due to weather, rain, night, and day in this example. So then how is this actually done in practice for this work? So the idea is to estimate the entropy over the visited states that the policy ends up visiting. And then using this particular entropy as the objective for the reward function for the reinforcement learning agent. However, one of the challenges here is it's very difficult to be able to estimate the state entropy for a particular policy. So what's done for this work in order to make it easier to be able to estimate and minimize this entropy using reinforcement learning is effectively the policy or the agent is conditioned on the sufficient statistics that describe the state history, the states that the agent has visited recently. And then now that the policy is conditioned on these sufficient statistics, this also helps produce a stationary MDP problem, so that the agent can basically understand how the environment is changing in this case and on how these statistics are changing. So let me give a more concrete example to help explain this. So here is an example using the game of Tetris. So here on the left, there's a video basically where we can see the agent operating in the environment, just placing different blocks around in the world. And then on the right here is the parameters that describe the sufficient statistics for this particular game. Here as just a Bernoulli distribution of block locations in the Tetris world. And then the reward function that the agent is going to be optimizing in this case is basically trying to find states in the future that'll have a very high likelihood under this these sufficient statistics or this distribution here that's shown on the right. And then after every state the agent visits, it now goes in and now it's going to update the parameters for these sufficient statistics in this case so that they'll be updated and be able to use in the next state that the agent visits. And then as a result, the agent will learn how states as a result of actions end up changing these statistics that describe basically the entropy of the states that the agent has visited. Right, so then here is an example of using SMIRL in order to minimize entropy on this VisDoom type task. So here the actual reward function is being visualized here on the right. And in this case, the agent learns how to avoid the number of fireballs that's being thrown at it from these kind of demon-looking agents and these weird worm monsters, and overall learns how to kind of minimize damage to itself in the process for this particular environment. I also run this on a couple of robotics types environments. So in this case, I'm taking a robot, putting it on the edge of a cliff or a pedestal, and then providing a number of kind of random external forces here. And as a result, the agent really wants to learn a good, robust balancing behavior so it doesn't end up tumbling off of this cliff here and falling to its doom, experiencing a lot of surprise on its way down. So then here, yes, to get into some of the comparisons between SMIRL and some of the curiosity type objectives. So here, SMIRL is being shown here as the black line in these graphs. And then so for these environments, for Tetris, for VisDoom, the SMIRL agent, when it's optimizing just for entropy, ends up getting better behavior in terms of some other qualitative metrics. So here, SMIRL ends up learning how to play Tetris while greatly reducing the number of deaths that the agent experiences in Tetris. Also greatly reduces the number of, or does increase the number of rows that are cleared for the Tetris environment. And then also here for the VisDoom environment, SMIRL ends up minimizing the entropy and as a result reduces the amount of damage on average that the agent takes in the environment. And then, yeah, so if you're also interested to know more about some of the curiosity-based measures here, it's a little bit of the opposite, where like applying curiosity-based measures on Tetris ends up in the agent learning many different unique ways in order to be able to fail in the game, basically. And then it's kind of similar for the Doom environment and for some of the robotics environments where curiosity measures result in the agent learning how to flop around on the ground in very different behaviors and not necessarily a type of stable behavior in the environment. So then one kind of challenge with using SMIRL is being able to estimate those sufficient statistics for more complex environments. And in this case, by complex, I really mean, very high dimensional state inputs, or even if they have very complex kinds of dynamics inside of the environment. So in order to be able to improve the learning speed on some of these environments, I can combine SMIRL with a type of learned and compressed representation that's learned using a variational autoencoder. So here, the original state space from the environment, so you can think of VisDoom, can be compressed down from something that's around 16,000 inputs to something that's around 128. And then here, the overall modification for the algorithm, as well as training the VAE online, basically for every state the agent visits, feed that through the encoder for the VAE, and this will produce a new latent. And now the SMIRL objective is actually learning to minimize the surprise over the distribution of latent states. And then here on the bottom, showing a couple of examples that indicate that in this case, this helps learn policies faster, even for some of the humanoid robotic examples in the environment. Then some of the insights from this work. So SMIRL works well in many of these environments for being able to develop different types of emergent behaviors. It's also really great because in this case, like SMIRL is a very task independent type of objective that you just want to be able to apply on an agent. And I can probably also say a little bit that a lot of the kind of motivation here is to be able to develop also reward functions that are entirely internal to the agent so that I can apply something like this on a robot and have it be able to learn in the real world without any kind of external information. It's just trying to minimize the observations that it sees in the world. And then I also, in this work, you can use different types of representation learning in order to be able to deal with some of the more complex inputs to make it easier to estimate theta and feed into the overall policy. And then, yeah, as I discussed a little bit, I really want to be able to apply this in more open and real worlds, and also even investigate more types of objectives like SMIRL and build on it. Because in this case, this worked in Tetris and VisDoom, but I would love if this would actually work in things like Minecraft. But this, and I'd be happy to talk more about that, but it's definitely a very large interest of mine. I'll skip forward so we can get going. So then discuss for a minute some additional future work that I'm very interested in. So basically, one of my future goals is really to focus more on task independent objectives. So kind of like how the SMIRL is a task independent objective, but my motivation here is really, I want agents to actually learn how to create tools inside of their environment the same way humans do create tools. Because in the process of creating a tool, it seems like we fundamentally know a lot more about how the environment works in a way such that if we create a tool, we know we can do something more or something faster inside of the environment. And then I'm also interested in doing types of automated task curriculum. So for some of the projects that I didn't have time to talk about, but being able to learn tasks in sequences and being able to generalize more and more to tasks into the future. If we can auto-generate sort of the difficulty of some of these tasks dependent on the current skill of the agent, we might be able to better control how quickly it learns and be able to learn a stronger agent overall. And so then for some of the other methods I'm also very interested in, I'm very interested in more work in hierarchical reinforcement learning. So in general, though, it's a little bit more about being able to actually learn the hierarchy in this case. So if we want really optimal policies that can get the highest reward, being able to find this kind of best communication structure or goal specification between policies, and then probably being able to construct a couple of different policies and learn this overall behavior will allow us to achieve even higher quality policies while still getting a lot of this kind of goal conditioned and functional reuse part of doing hierarchical reinforcement learning. And then I'm also very interested in doing types of lifelong learning algorithms. So basically being able to have an agent continually learn and integrate and understand that it should generalize some of its skills. And I'm currently applying types of meta learning in order to be able to speed up some types of continual learning. And I'm extremely grateful to all the collaborators that I've been very fortunate to work with over kind of my years of doing research. And that's my story for today. And I'd be more than happy to answer some more questions or have any more discussion. Thank you.